Okay, so we talked about the graphs. Now, how do we traverse the graph? There are different. Okay, so let's talk about a graph traversal algorithm, BFS. Already, probably you know that BFS is breadth first search, right? So we did it in traversing a tree, and we know that a tree is a special kind of graph, right? It's also a set of vertices and edges, where the edges have constraints. So using BFS, I can also traverse any graph, but it's a little bit different than what I'm doing in a tree. It's almost the same, just a little bit difference. The difference, the reason behind that is, say, when you're actually doing a tree, right? So this was an example of a tree, right? So when you are doing the BFS, we are putting this into the queue and then putting the neighbors. So we're putting the neighbors, right? And done. There was no way. So not neighbors, actually. That was the mistake I'm thinking. So we are putting the children, right? In a tree, all the adjacent nodes are children, whereas in a graph, it's neighbors. So what happens? What is the difference? So in a tree, what we do is when you're working with parent, we take out the parent and put the children in the queue, right? So this is child 1, child 2, child 3. So what happens is when you actually take out the child, we never bring back the parent, right? We always go down the child. So do you get it? So when you are actually working with a child, we don't get back to the parent. We are just going down or something, right? When you are working with B, next time we are going to work with E and F. But in a graph, what happens is there is no parent-child concept. Everything is a neighbor, right? So once you have started BFS on a node, and then you start working on your neighbors, that's fine. But later on, when you are actually working on your neighbor also thinks, oh, okay, one is my neighbor, so I should work on it. But already work on one is done, right? So you have to keep track which one is visited and which one is not. Okay, so in a tree, we are doing it implicitly. Whenever we are taking something out of the queue, we're saying it's visited. But here, we have to have specific markers to say like whether a node is visited or not. Okay, so let's look at one example. So we know that for BFS, we use queue, right? So this is a queue. That's one thing. And we said like we have to have something to keep track of the visited, the nodes that are visited, so that we don't come back again to the same node. Because once we are processing A, right, we will put B and C into the queue. That is fine. But next time when you're actually doing processing B, there should be a marker that A already has been processed, so that B doesn't bring back A into the queue, right? Okay, so we actually have a visited list, and then we have a queue, and the graph is, so let's say this is we have an adjacency list representation. Okay, so that means each node will have a list of its edges or neighbors. So this will be B, C, D. For B, it's going to be A, E, right? So this is the representation of the graph. For C, it's going to be A and D. For D, it's going to be B and E, right? Oh, sorry, A, B, and E. And for E, the adjacent vertices are going to be B and D. So this is the graph representation that we got. Now, what we are going to do is we start somewhere. Say we put A. We start here. Okay, so we put A into the queue, and then we take out A, right? Once we take out A, okay, let's say this is the visit order. Okay, so we take out A. As soon as we take out A, what we do is we add A into the visited list and put A's neighbors. What are the A's neighbors? B and C and D, right? These three, B, C, and D. We take the A's, we take A out and put A's neighbors into the queue. Okay, so next time I'm taking B out. Okay, that's fine. I'm taking B out. And I have to put B into the visited list. And then I have to go to B's neighbors and put them into the queue. But the thing is, before putting A into the queue, I will check if A is already in the visited list. If any of my neighbors are already into the visited list, so I'm not going to put it into the queue. I see that A is in my neighbors list, but A is already visited here in the visited list. So I don't put A again. Instead, I see I want to put E, and E is not in the visited list, so I put E, right? So next time I take out C, I add C to the visited list, and then I take a look at C's neighbors. So you see C's neighbors are A and D. Okay, so I probably made a mistake here. So whenever I am actually putting something into the, okay, so the mistake here is actually whenever I'm putting something into the key, immediately I have to put it into the visited list, not taking it out. Okay, so let's repeat again. Okay, so I was putting A, into the list and putting A into the visited list. And then I was taking, whenever I'm taking A out, I am now putting my neighbors. So I'm checking if my neighbors are already into the visited list. None of them are. So I put B and then C and then D. And I put B, C, D. Whenever I'm putting into the queue, I also put into the visited list. Then I take out B and check B's neighbors, which is A and E. A is already into the visited list, so I don't put it into the queue, but E is not, right? So I put it into the queue and put E into the visited list. Next, I take C out and I check C's neighbors A and D. You see both A and D are in the visited list, so I don't put any of them into the queue. So next, I take out D. These neighbors are A, B, and E. You see all three are already in the visited list, right? So I don't put any of them into the queue again. Okay, next I take out E, and E's neighbors are B and D. So before I want to put B and D into the queue, I check in the visited list, and I see B and D are already in the visited list. That means I don't put them. Okay, so this is important, keeping a separate visited list so that the already visited nodes are not visited again. So that is the BFS algorithm, right? just the same way you learned before. The only thing is whenever you are putting something into the queue, you also put it, sorry, you also put it into the visited list. Okay, so what is the runtime of BFS algorithm on a graph? So this is a pseudocode for BFS. You see, initially we have a queue. We initiate a queue, right? And then we have a visited set or map. So we start with enqueuing any node, right? And mark enqueuing any node X and mark that node X as visited. Also, you can say like by marking X visited means adding X to the visited set or map. Then until the queue is not empty, I dequeue from the top of the queue. So we dequeue, say, Y from the top of the queue. And for all unvisited neighbors of Y, which we call Z or Z, we mark Z visited and also enqueue Z. Okay, so here is the important thing. When we are actually dequeuing something, or say dequeuing Y from the queue, we're looking for all the neighbors of Y, which we say are Z. And then we enqueue them and mark them visited. So where do we find these neighbors? We get it from this adjacency list, right? So this adjacency list is the representation of the graph. So when you are actually given the input graph, probably you are given it in the adjacency list format. Okay, so let's try to find the runtime of the algorithm, like time and space complexity of the algorithm. You see here that these, like, all these things are like constant time operations, right? These are constant time operations. This is done just once, but this while loop, how many times this while loop runs? Well, this while loop may run like v times, where v is the number of vertices of the graph, right? So that means this may run v times. And how many times this for loop run? So in total, this for loop runs order of e time, because throughout the graph, like the graph in total has e edges. That means if I go to different vertices and check for edges, in total I will be exploring like e edges, right? Okay, so that means the total amount of work in these while loop is order of v plus order of e. Or we can say the time complexity of the algorithm is order of v plus e. So that is the time complexity of BFS algorithm for a generic graph. Okay, and then let's say, what is the space complexity? So this is the time complexity. Now the space complexity, how much is extra space we need. So you see here that in the queue, at most we may need to put, say, v space, like all the nodes go into the queue at the same time. So it might be order of v, the size of the queue. Also, this visitor set will contain like v nodes, right? So order of v plus order of v, that means the space complexity is going to be order of v.